Welcome to the Explainer. I am so incredibly glad you're here today because we are looking at something absolutely mind-boggling. We're going to explore the sheer, unbelievable scale of open ocean salmon farming. Just think about it. We are taking one of the most dynamic, unpredictable, and powerful forces on Earth, the open ocean, and engineering a way to safely raise millions of delicate fish right in the middle of it. Today, we're going to zoom all the way out to look at the massive oceanic forces at play, and then we're going to scale all the way down to the careful delivery of a single tiny fish. It is quite literally a masterpiece of biology and engineering working together.
Okay, let's dive into this. Our spatial blueprint for today is pretty straightforward. We'll start with moving to the ocean, then finding the perfect location, battling the elements, engineering the sea farm, and we'll wrap it all up with delivering the salmon.
All right, Section 1, moving to the ocean. Let's get into it.
So, salmon are born in freshwater, right? But they grow up in the salty ocean. To make that switch, they go through this wild biological process called smoltification. Their gills literally undergo inner modifications to pump out excess salts so they can actually survive in seawater. But, and this is a massive but, timing is absolutely everything. It's a ticking biological clock. If farmers don't get these fish into the seawater during a very specific window, well, they undergo desmoltification. They completely lose those critical saltwater adaptations, meaning they can no longer process the salt, and bam, the window closes. Now you might be wondering, why not just keep them in tanks on land? Well, this perfectly illustrates why we rely so heavily on the open ocean. When we compare land-based aquaculture to open sea cages, the differences are night and day. Land-based systems give you incredible control, for sure, but they require a massive upfront investment. Huge plots of land, and they rely completely on pumps running 24/7, 365 days a year. Power goes out, backup generator fails, you lose everything. Open sea cages, on the other hand, utilize the awesome power of nature. Ocean currents act like a free, non-stop delivery service for oxygen while simultaneously whisking away carbon dioxide and waste. It's a total no-brainer why the open sea is the dominant choice for modern salmon farming.
Which brings us perfectly to Section 2, finding the perfect location. We found the perfect stretch of ocean, but how do we know it's actually safe?
Check out this intense quote directly from our source material. If such anoxic conditions develop under sea cages, you will literally be sitting on a ticking bomb. Seriously, a ticking bomb. What that means is depth and water flow are quite literally life and death. If the water is too shallow or the currents are just too weak, fish waste and uneaten feed just pile up on the seafloor. This overwhelms the natural microbes, strips the oxygen from the bottom, and creates an anoxic environment. And when that happens, a new type of bacteria takes over, one that spits out hydrogen sulfide gas. Smells exactly like rotten eggs, and even in tiny concentrations, it is highly toxic and completely fatal to salmon. So you absolutely have to place these farms in locations with enough depth and current to sweep all that waste away.
The other huge factor for a perfect location is temperature. Temperature dictates almost everything about a fish's growth. The absolute sweet spot, the optimal growth zone, is between 12 and 14 degrees Celsius. Now, salmon are super tough. They can handle the cold. But once the water dips below 4 degrees, their growth practically hits a brick wall. Their immune system slows way down, and they lose the ability to heal from even simple abrasions. Anything under 2 degrees? Yeah, that is firmly in the danger zone.
All right, let's shift gears to Section 3, battling the elements. We are talking about immense, powerful water movements that these farms have to survive. Major ocean currents, tidal currents pulled by the moon, local fjord systems, wind-driven surface currents. It is a highly dynamic environment. But get this, it's actually the North Atlantic drift, this massive, warm ocean current that makes it possible for Norway to farm salmon all the way up at 70 degrees north latitude. Without that specific ocean current, farming that far north would be completely out of the question.
But, these currents aren't just trying to wreck the farm structure. They're actually amazing for the fish. Think of it as fish cardio. A minimum current of about 5 centimeters per second doesn't just flush out the waste, it actively forces the salmon to swim against the flow. This giant aquatic treadmill ramps up their appetite, boosts their growth, and ultimately gives you a way higher flesh quality at the end of the day.
Of course, liquid water isn't the only element we're battling here. We've got to deal with frozen water, too. The threats come in 3 main forms: surface ice, drift ice, and the actual icing over of the farm equipment itself. Now, drift ice is literally terrifying for a fish farmer, because when you see a chunk of drift ice floating towards your farm, you're only seeing 1/10 of its actual mass. The other 9/10 are hidden underwater, acting like this giant sail catching the ocean currents. It becomes an unstoppable battering ram that can easily crush a mooring system.
Now, what's really interesting about this slide is this specific number, -1.9 degrees Celsius. Why does that matter? Well, fresh water freezes at 0 degrees, right? But seawater, because it's super salty, about 35 parts per thousand, doesn't actually freeze until it hits exactly -1.9 degrees Celsius. That tiny little buffer is absolutely vital for farmers when they're monitoring surface ice formation during those brutal winter months.
Moving right along to Section 4, Engineering the Sea Farm. So, the crucial point is, how do we build a structure that survives all of these brutal elements?
It all starts at the very bottom, anchoring this massive setup to the seafloor. We generally use two distinct strategies. On one side, we have drag embedment anchors. These are wild. They're designed so that the harder the ocean pulls on the farm, the deeper the anchor digs into the seabed. On the other side, we have weighted anchors, which are usually massive blocks of iron-reinforced concrete. These are perfect for a soft, muddy bottom. They rely entirely on their sheer immense weight, sinking deep into the mud and acting like a giant suction cup holding the whole shebang in place.
But an anchor is totally useless without the proper mooring line. And in marine aquaculture, there is a golden rule of geometry. The length of the mooring line has to be at least 3 times the depth of the water.
Let's actually walk through the math to see exactly how that plays out. Say you find an awesome location and the water under your cages is 60 meters deep. Multiply that by 3, and that means you need a staggering 180 meters of mooring line just for one single anchor. Why so much? Because you need the force pulling on that anchor to be as horizontal as possible. Otherwise, during a bad storm, it would just rip straight up and out of the seabed.
And that mooring system isn't just a bunch of ropes. We're talking massive, heavy steel chains. But the chain isn't just there for brute strength. Its sheer, sagging weight actually acts like a giant shock-absorbing spring. When a massive wave slams the surface cage, the cage yanks on the line. But instead of snapping a tight rope, it simply lifts that heavy chain slightly off the seafloor. The chain buffers the bounce, absorbs all that crazy kinetic energy, and stops the sea cage from just shattering in rough, choppy seas. It's such an elegant physical solution to a totally violent natural problem.
And finally, Section 5, Delivering the Salmon. We've zoomed all the way in. The farm is built, the water is tested, and now the delicate smolt are arriving.
Let's move to and see how this builds into a super strict, highly controlled delivery protocol. The smolts are usually delivered by wellboats. First things first, you obsessively check the weather. Then you verify the transporter logs to make sure the water quality was perfect during the whole trip. But step 3 is the critical one. You absolutely must moor the boat far away from the cages. If a wellboat gets too close, its powerful side propellers, the thrusters, can create such massive suction that they will literally suck the farm's nets right into the spinning blades, causing a catastrophic escape. So, once you're secured at a safe distance, the fish are unloaded as gently as humanly possible.
The second those smolts are in their new ocean home, they are highly stressed out. I mean, the transition is dramatic. So there's a simple but totally vital rule for feeding. It has to be done in frequent but very small portions. You have to ensure the food is spread out evenly across the surface so that every single fish, no matter how stressed, gets a bite and starts to recover its strength.
In those first few crucial days, farmers become meticulous observers. The golden rule here is to keep a super close watch on the lee side of the cage. That's the down current side. Why? Because fish that haven't successfully finished smoltification or are just struggling with the big move won't have the strength to swim against the current. They will predictably drift and clump together on that down current side. If a farmer spots these floaters, they know instantly that they need to call in a vet and intervene.
We have scaled from the massive, sweeping forces of global ocean currents all the way down to a struggling smolt on the lee side of a net. We've seen the absolute engineering marvel it takes to safely merge fragile biology with the wild sea. But here's the thing. As coastal waters get more crowded, and as we chase better currents and cleaner water, nature is pushing these incredible structures further and further out into the open ocean. Which leaves us with a final, pretty awe-inspiring question to consider. As our engineering gets stronger and our understanding of biology gets deeper, how far out into the ocean can we really go? Thank you so much for joining me on this explainer, and keep wondering,